Level 1. Mechanics. Mechanics is the branch of physics that deals with the motion of objects and the forces acting on them. It lays the foundation for understanding how objects move, interact, and respond to external forces. Mechanics is divided into two main categories: kinematics and dynamics. Kinematics describes motion without considering its causes, while dynamics focuses on the forces that produce motion. This field is essential for studying everything from the movement of celestial bodies to the mechanics of machines. One of the earliest contributors to mechanics was Aristotle, who believed that objects moved according to their nature. However, this view was later challenged by Galileo Galilei, who introduced the concept of inertia, which states that an object in motion stays in motion unless acted upon by an external force. This laid the groundwork for Isaac Newton's 3 laws of motion, which revolutionized our understanding of mechanics. Newtonian mechanics, also known as classical mechanics, describes motion at speeds much lower than the speed of light. It is accurate enough to explain most everyday phenomena, like falling objects, vehicle movement, and planetary orbits. However, it does not hold at extremely high speeds or at the atomic scale, where relativistic mechanics and quantum mechanics become relevant. One fundamental concept in mechanics is displacement, which describes an object's change in position. Unlike distance, displacement is a vector quantity with both magnitude and direction. This distinction becomes crucial when calculating other physical quantities like velocity and acceleration. Velocity is another key concept, defined as the rate of change of displacement over time. It differs from speed, which is scalar and does not consider direction. Acceleration, on the other hand, measures the rate of change of velocity. Understanding these 3 quantities is vital for analyzing any motion. Newton's second law of motion introduces the concept of force, defining it as the product of mass and acceleration. This relationship explains why heavier objects require more force to accelerate and forms the basis for analyzing dynamic systems. Forces can be contact-based, like friction, or action at a distance, like gravity. Work and energy are also fundamental aspects of mechanics. Work is done when a force causes an object to move, while energy is the capacity to perform work. Kinetic energy is associated with motion, whereas potential energy is related to an object's position within a force field, such as gravitational or elastic potential energy. Finally, the law of conservation of energy states that energy cannot be created or destroyed, only transformed. This principle is crucial for solving mechanical problems, as it provides a powerful tool for tracking energy flow within a system. Understanding mechanics is thus essential for exploring more complex topics in physics. Level 2. Kinematics. Kinematics is the branch of mechanics that describes the motion of objects without considering the forces that cause them. It focuses on quantities like displacement, velocity, acceleration, and time. By analyzing these variables, kinematics provides a mathematical framework for predicting future motion. This makes it a foundational topic in physics, relevant to everything from everyday movement to planetary orbits. One of the first steps in kinematic analysis is defining a reference point from which an object's position is measured. Position is a vector quantity, having both magnitude and direction. The change in position over time is called displacement, another vector quantity distinct from distance, which is scalar and does not account for direction. Velocity is the rate of change of displacement with respect to time. It is also a vector, meaning it has both magnitude and direction. Instantaneous velocity describes the speed and direction of an object at a specific moment, while average velocity is calculated over a time interval. Acceleration is the rate of change of velocity over time. Positive acceleration means an object is speeding up, while negative acceleration or deceleration indicates slowing down. Just like velocity, acceleration is a vector quantity. In uniformly accelerated motion, acceleration remains constant, leading to straightforward kinematic equations. The 3 main kinematic equations are essential tools for solving motion problems. They relate displacement, initial velocity, final velocity, acceleration, and time. These equations assume constant acceleration, making them particularly useful for analyzing free-falling objects where gravitational acceleration is constant. Projectile motion is a special case of 2-dimensional kinematics. It involves objects moving under the influence of gravity, while maintaining a horizontal velocity. This motion can be broken down into horizontal and vertical components, analyzed separately using kinematic equations. Examples include a thrown ball, a bullet's trajectory, or a diver's jump. Circular motion is another key aspect of kinematics. When an object moves along a circular path, its velocity vector constantly changes direction, resulting in centripetal acceleration. This inward acceleration keeps the object in circular motion and is calculated using the formula where is velocity and is the radius of the circular path. Kinematics is fundamental for understanding more complex motion scenarios and forms the basis for dynamics, where the forces causing motion are examined. By mastering kinematics, one gains a powerful toolkit for analyzing real-world problems, from sports physics to celestial mechanics. Level 3. Dynamics. Dynamics is the branch of mechanics that studies the forces that cause motion. Unlike kinematics, which describes motion without considering its causes, dynamics explores the relationship between motion and the forces affecting it. This branch of physics provides insight into why objects move the way they do, making it essential for understanding real-world phenomena. The foundation of dynamics is laid by Newton's 3 laws of motion. The first law, or the law of inertia, states that an object remains at rest or in uniform motion unless acted upon by an external force. This principle explains why seatbelts are crucial during a sudden stop. Passengers continue moving forward due to inertia. Newton's second law of motion is the cornerstone of dynamics. It states that the force acting on an object is equal to its mass, multiplied by its acceleration. This law quantifies the effect of forces on an object's motion and allows for the calculation of unknown variables, making it a powerful tool for solving dynamics problems. The third law of motion asserts that for every action, there is an equal and opposite reaction. This explains phenomena like rocket propulsion, where the expulsion of gases generates an equal force pushing the rocket forward. It also accounts for the recoil felt when firing a gun. Friction is a key force studied in dynamics. It opposes motion and arises due to the contact between surfaces. Static friction prevents objects from moving, while kinetic friction opposes moving objects. The magnitude of friction depends on the nature of the surfaces and the normal force pressing them together. Tension forces occur in ropes, cables, or strings transmitting force. These forces always pull away from the object and are analyzed using free body diagrams. Dynamics also considers forces like gravity, normal forces, and applied forces, all of which contribute to an object's motion. Dynamics extends into rotational motion, where forces produce torques that cause objects to rotate. The rotational analog of Newton's second law is where is torque is the moment of inertia and is angular acceleration. This helps explain phenomena like spinning tops or the motion of celestial bodies. Understanding dynamics is crucial for engineering applications, vehicle safety, sports physics, and even space travel. By studying the forces behind motion, dynamics provides a comprehensive understanding of how the physical world operates. Level 4. Newton's laws of motion. Newton's laws of motion are fundamental principles that form the basis of classical mechanics. Formulated by Sir Isaac Newton in his landmark work, Philosophiae Naturalis Principia Mathematica in 1687, these laws describe the relationship between the motion of an object and the forces acting on it. They apply to all objects, from microscopic particles to massive celestial bodies, under conditions where relativistic effects are negligible. The first law, known as the law of inertia, states that an object at rest stays at rest, and an object in motion continues in a straight line at a constant velocity unless acted upon by an external force. This concept was revolutionary because it contradicted the Aristotelian view that objects required a force to maintain motion. The first law emphasizes the natural tendency of objects to resist changes in their state of motion, which is defined as inertia. The second law of motion provides a quantitative description of the effect of force on an object's motion. It states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass, expressed mathematically as. This law explains why heavier objects require more force to accelerate and is essential for analyzing dynamic systems in engineering and physics. Newton's third law states that for every action, there is an equal and opposite reaction. This means that forces always occur in pairs. If object A exerts a force on object B, then object B exerts an equal and opposite force on object A. This principle explains phenomena such as rocket propulsion, where the expulsion of gases produces a reactive force that propels the rocket forward. These laws are interconnected and provide a comprehensive framework for understanding motion. For example, the second law explains how forces change an object's motion, while the first law describes the state of motion in the absence of net external forces. The third law ensures that forces are balanced, maintaining the consistency of motion within isolated systems. Applications of Newton's laws are vast and diverse. In everyday life, they explain why seat belts are necessary in cars, first law, how pushing a heavy box requires more effort than pushing a lighter one, second law, and why swimmers propel themselves forward by pushing water backward, third law. Engineers use these laws to design structures, vehicles, and machines that can withstand forces and function efficiently. In celestial mechanics, Newton's laws explain the motion of planets, moons, and artificial satellites. By applying his laws to gravitational forces, Newton demonstrated that the same principles governing motion on Earth also apply to heavenly bodies, unifying terrestrial and celestial mechanics. This realization laid the foundation for modern astrophysics and space exploration. Despite their success, Newton's laws are not universally applicable. At very high velocities, approaching the speed of light, or on atomic scales, relativistic mechanics and quantum mechanics provide more accurate descriptions. Nevertheless, Newton's laws remain indispensable for most practical applications, making them a cornerstone of classical physics. Level 5. Friction. Friction is a resistive force that opposes the relative motion between two surfaces in contact. It is an essential aspect of everyday life, enabling activities like walking, driving, and gripping objects. Without friction, objects would continue to move indefinitely once set in motion, and it would be impossible to control or stop their movement. Friction is categorized into several types, including static, kinetic, and rolling friction, each with distinct characteristics. Static friction acts on an object at rest, preventing it from moving until a sufficient force is applied. It is generally stronger than kinetic friction, which occurs when an object is already in motion. This explains why it is harder to start pushing a stationary object than to keep it moving. The maximum value of static friction is proportional to the normal force exerted by the object on the surface, represented by the equation, where is the coefficient of static friction, and is the normal force. Kinetic friction, on the other hand, opposes the motion of an object sliding over a surface. It is generally constant regardless of speed and is given by where is the coefficient of kinetic friction. This force is responsible for slowing down moving objects and generating heat due to the interaction between surfaces at the microscopic level. Rolling friction occurs when an object rolls over a surface, such as a wheel or a ball. It is typically much smaller than kinetic friction, which is why wheels and ball bearings are used to minimize resistance and facilitate smoother motion. Rolling friction depends on factors like the object's weight, surface texture, and the deformation of the surfaces in contact. Friction is primarily caused by the microscopic irregularities on surfaces, which interlock and resist relative motion. At a molecular level, adhesive forces between the atoms of the surfaces also contribute to friction. This complex interaction makes friction a challenging phenomenon to model accurately, especially in non-ideal conditions. While friction is often perceived as a hindrance, it is crucial for many practical applications. Without friction, cars would be unable to accelerate, decelerate, or navigate turns. Walking would be impossible as there would be no grip between our feet and the ground. In sports, friction is necessary for athletes to change direction, stop suddenly, or maintain control over equipment. However, friction also has undesirable effects such as wear and tear on mechanical parts, energy loss as heat, and reduced efficiency in engines. To counteract these issues, lubricants like oil and grease are used to minimize friction in moving components, extending their lifespan and enhancing performance. Understanding friction is vital for engineers and designers. In automotive engineering, friction is carefully balanced to ensure optimal tire grip and braking efficiency. In aerospace applications, minimizing friction is essential for reducing drag and increasing fuel efficiency. Industrial machinery relies on precise friction control to maintain safety and productivity. Despite its familiarity, friction remains an area of active research, particularly at the nanoscale, where traditional models break down. Advances in nanotechnology and materials science continue to provide new insights into friction's underlying mechanisms, leading to innovative solutions for real-world challenges. Level 6. Work, energy, and power. Work, energy, and power are fundamental concepts in physics that describe the transfer and transformation of energy within a system. These quantities are interconnected and provide a framework for analyzing mechanical systems, thermodynamics, and even electromagnetic phenomena. Understanding them is crucial for solving problems related to motion, machines, and energy conservation. Work is done when a force acts on an object and causes it to move in the direction of the force. It is calculated using the formula, where is work, is the force, is the displacement, and is the angle between the force and displacement vectors. Work is measured in joules J and is a scalar quantity. If the force is perpendicular to the displacement, no work is done. Energy is the capacity to do work. It exists in various forms, including kinetic energy, potential energy, thermal energy, and chemical energy. Kinetic energy is associated with motion and is given by the formula where is mass and is velocity. Potential energy, on the other hand, is stored energy due to an object's position or configuration, such as gravitational potential energy or elastic potential energy. The law of conservation of energy states that energy cannot be created or destroyed, only transformed from one form to another. This principle is fundamental in physics, allowing the tracking of energy flow within a system. For example, in a pendulum, kinetic energy is converted to potential energy and vice versa, but the total mechanical energy remains constant, assuming no energy loss due to friction or air resistance. Power is the rate at which work is done or energy is transferred. It is calculated using the formula, whereas power is work and is time. Power is measured in watts, W, where 1 watt equals 1 joule per second. In practical applications, power indicates the efficiency and performance of machines, engines, and electrical devices. The concept of mechanical advantage is closely related to work and energy. It describes how machines like levers, pulleys, and gears amplify an applied force, making tasks easier to perform. These simple machines do not change the total work done, but allow force and distance to be traded off, demonstrating the conservation of energy principle. Energy efficiency is a key consideration in real-world applications, where some energy is inevitably lost as heat due to friction or resistance. Understanding the relationship between work, energy, and power enables engineers to design more efficient machines and systems, reducing energy waste and optimizing performance. In thermodynamics, work, energy, and power are crucial for analyzing heat engines, refrigerators, and other systems that convert thermal energy into mechanical work. The study of energy transformations underpins the development of sustainable energy sources and technologies, such as solar panels, wind turbines, and electric vehicles. These concepts extend beyond mechanics and thermodynamics to other fields of physics, including electromagnetism and quantum mechanics. Mastery of work, energy, and power provides a solid foundation for exploring more advanced topics, making them essential for students and professionals in science and engineering. Level 7. Momentum and impulse. Momentum and impulse are key concepts in physics that describe the motion of objects and how they change when forces are applied. Momentum is a measure of an object's motion, while impulse quantifies the change in momentum due to a force over a period of time. These concepts are particularly useful for analyzing collisions, explosions, and other interactions between objects. Momentum is defined as the product of an object's mass and velocity, given by the equation, whereas momentum is mass and is velocity. It is a vector quantity, meaning it has both magnitude and direction. Momentum plays a crucial role in understanding motion as it describes an object's resistance to changes in its state of motion. The law of conservation of momentum states that the total momentum of an isolated system remains constant unless acted upon by an external force. This principle is fundamental for analyzing collisions and explosions, where the total momentum before and after the event is conserved. It applies to both elastic collisions, where kinetic energy is also conserved, and inelastic collisions, where objects stick together and kinetic energy is not conserved. Impulse is defined as the product of force and the time interval over which it acts, expressed as whereas impulse is force and is the time interval. Impulse is also a vector quantity and is directly related to the change in momentum, as stated by the impulse-momentum theorem. This equation explains why extending the time of impact, such as bending knees when landing, reduces the force experienced. Impulse and momentum are crucial for understanding collisions. In car crashes, crumple zones are designed to increase the time of impact, thereby reducing the force on passengers. Similarly, airbags reduce injuries by prolonging the collision duration, demonstrating the practical applications of impulse in safety engineering. Angular momentum is a rotational analog of linear momentum, describing the rotational motion of objects. It is calculated using the formula, whereas angular momentum is the moment of inertia and is angular velocity. Angular momentum is also conserved in isolated systems, explaining phenomena like a figure skater spinning faster when pulling in their arms. In sports, momentum and impulse play significant roles. A footballer kicking a ball imparts an impulse, changing its momentum. In boxing, a punch's impact is determined by the momentum transferred. Understanding these principles enhances athletic performance and safety equipment design. In astrophysics, momentum and impulse are crucial for analyzing celestial collisions, orbital mechanics, and the formation of planetary systems. The conservation of angular momentum explains why planets rotate and why accretion disks form around black holes. Mastering momentum and impulse provides a deeper understanding of motion and force interactions. These principles bridge the gap between kinematics and dynamics, paving the way for more advanced topics in mechanics and physics. Level 8. Circular motion. Circular motion occurs when an object moves along a curved path or a circular trajectory. It is a fundamental concept in physics, describing the motion of planets, satellites, amusement park rides, and even particles and accelerators. Circular motion can be uniform, where the speed is constant, or non-uniform, where the speed varies. Understanding circular motion involves analyzing forces, velocity, and acceleration, which are directed toward the center of the circular path. In uniform circular motion, an object moves at a constant speed along a circular path. However, its velocity continuously changes direction, pointing tangentially to the circle at every point. This change in direction implies the presence of acceleration, known as centripetal acceleration, directed toward the center of the circle. The magnitude of this acceleration is given by where is the speed and is the radius of the circular path. Centripetal force is the net force required to keep an object moving in a circular path. It acts toward the center of the circle, maintaining the object's curved trajectory. According to Newton's second law, centripetal force is calculated as where is the object's mass. This force can be provided by tension, gravity, friction, or other forces depending on the context. Examples of circular motion are abundant in everyday life. A car turning around a curve experiences centripetal force due to friction between the tires and the road. In planetary orbits, gravity provides the necessary centripetal force, keeping planets in elliptical paths around the Sun. Similarly, artificial satellites are kept in orbit by the gravitational pull of the Earth, balancing centripetal force and inertia. Non-uniform circular motion occurs when the speed of the object changes, resulting in both radial, centripetal, and tangential acceleration. Tangential acceleration is responsible for changing the object's speed, while centripetal acceleration changes its direction. This type of motion is observed in roller coasters and cars accelerating or decelerating while navigating curves. Angular velocity and angular acceleration are crucial for analyzing circular motion. Angular velocity describes how quickly an object rotates around a point, measured in radians per second. Angular acceleration measures the rate of change of angular velocity. These quantities are related to linear velocity and acceleration through the radius of the circular path. Centrifugal force is a perceived force experienced in a rotating reference frame, directed outward from the center of rotation. It is not an actual force, but an effect of inertia, giving the sensation of being pushed outward while in circular motion, such as in a spinning amusement ride or a turning car. Circular motion is essential for understanding rotational dynamics, orbital mechanics, and gyroscopic effects. Engineers use these principles to design safe curves in roads, amusement park rides, and even centrifuges in laboratories. Mastery of circular motion lays the groundwork for exploring more complex rotational systems and dynamics. Level 9. Gravitation. Gravitation is a universal force of attraction that acts between all objects with mass. It governs the motion of planets, stars, galaxies, and even light under extreme conditions. The study of gravitation has led to groundbreaking discoveries in physics, from Newton's law of universal gravitation to Einstein's theory of general relativity. Gravitation is fundamental to our understanding of the universe's structure and dynamics. Newton's law of universal gravitation states that every mass attracts every other mass with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Mathematically, it is expressed as, where is the gravitational force, and are the masses, is the distance between them, and is the gravitational constant. This inverse square law explains why the gravitational force decreases rapidly with increasing distance. It also accounts for the elliptical orbits of planets, as described by Kepler's laws of planetary motion. Newton's formulation unified terrestrial and celestial mechanics, showing that the same force responsible for an apple falling to the ground governs the motion of the moon and planets. Gravitational acceleration on Earth, denoted as mbo, is approximately near the surface. It varies slightly with altitude, latitude, and local geological formations. This acceleration is responsible for the weight of objects and influences the motion of projectiles, pendulums, and freely falling bodies. Gravitational potential energy is the energy stored in an object due to its position in a gravitational field. It is given by near-Earth's surface, whereas mass is gravitational acceleration and is height. In a more general context, it is expressed as emphasizing the attractive nature of gravity. Einstein's theory of general relativity revolutionized our understanding of gravitation. It describes gravity not as a force, but as a curvature of spacetime caused by mass and energy. According to general relativity, massive objects like planets and stars warp the fabric of spacetime, influencing the motion of other objects and even light. This has been confirmed through phenomena such as gravitational lensing and the precession of Mercury's orbit. Gravitational waves, predicted by general relativity and detected by LIGO in 2015, are ripples in spacetime generated by accelerating massive objects, such as colliding black holes or neutron stars. Their detection opened a new window for observing the universe and confirming Einstein's predictions with unprecedented precision. Gravitation influences the large-scale structure of the universe, from galaxy formation to the expansion of space itself. It governs the dynamics of cosmic objects, determines the fate of stars, and shapes the evolution of galaxies and clusters. Understanding gravitation is crucial for cosmology, astrophysics, and space exploration. Despite its pervasive influence, gravity is the weakest of the four fundamental forces, and its integration with quantum mechanics remains an open challenge in physics. The quest for a quantum theory of gravity, possibly through string theory or loop quantum gravity, continues to be one of the greatest scientific endeavors of our time. Level 10. Fluid Mechanics. Fluid mechanics is the branch of physics that studies the behavior of fluids, liquids, gases, and plasmas, and the forces acting on them. It is fundamental to understanding phenomena ranging from blood flow in the human body to atmospheric dynamics and ocean currents. Fluid mechanics is divided into fluid statics, which studies fluids at rest, and fluid dynamics, which examines fluids in motion. In fluid statics, the key concept is pressure, defined as the force exerted per unit area. Pressure in a fluid at rest increases with depth due to the weight of the fluid above. This is described by the hydrostatic pressure equation, whereas the pressure at depth is the surface pressure, is fluid density, is gravitational acceleration, and is depth. This principle explains why submarines and deep-sea creatures must withstand enormous pressures. Pascal's principle states that a change in pressure applied to an enclosed fluid is transmitted undiminished to all parts of the fluid and the container's walls. This principle is the basis for hydraulic systems, such as car brakes and hydraulic lifts, where a small force applied to a piston is amplified to lift heavy loads. Archimedes' principle explains buoyancy, stating that an object submerged in a fluid experiences an upward buoyant force equal to the weight of the fluid displaced. This explains why ships float, why balloons rise, and why objects feel lighter underwater. It also provides the basis for calculating the volume and density of irregular objects using water displacement. Fluid dynamics studies fluids in motion, characterized by velocity, pressure, and density variations. The continuity equation expresses the conservation of mass in fluid flow, where is the cross-sectional area and is the velocity. It shows that fluid speed increases as the cross-sectional area decreases, as observed in nozzles and river narrows. Bernoulli's principle relates the pressure, velocity, and height of a moving fluid, expressed as. It explains the lift on airplane wings, the functioning of carburetors and atomizers, and the curve of a spinning ball. Bernoulli's equation demonstrates the inverse relationship between pressure and velocity in a streamlined flow. Viscosity is a measure of a fluid's resistance to flow. High viscosity fluids, like honey, flow slowly, while low viscosity fluids, like water, flow easily. Viscosity influences drag forces on objects moving through fluids and affects fluid flow in pipes, governed by Poiseuille's law. Turbulence, a chaotic flow pattern, occurs at high velocities or in complex geometries, complicating fluid dynamics calculations. Applications of fluid mechanics are vast, including meteorology, oceanography, aerodynamics, hydraulics, and medical sciences. It is essential for designing pumps, turbines, aircraft, ships, and pipelines. In medicine, fluid mechanics helps understand blood circulation and respiratory airflow, contributing to biomedical device design. Fluid mechanics continues to be a dynamic field of research, addressing complex phenomena like fluid structure interactions, non-Newtonian fluids, and multiphase flows. Advances in computational fluid dynamics, CFD, enable simulations of fluid behavior in engineering, environmental science, and astrophysics, driving innovation and discovery. Level 11. Thermodynamics. Thermodynamics is the study of heat, energy, and work, and their interactions in physical systems. It explains how energy is transferred and transformed, governing the behavior of engines, refrigerators, power plants, and even biological systems. Thermodynamics is based on 4 fundamental laws, known as the zeroth, first, second, and third laws of thermodynamics. The zeroth law of thermodynamics establishes the concept of temperature. It states that if 2 systems are each in thermal equilibrium with a third system, they are in thermal equilibrium with each other. This implies that all 3 systems share the same temperature, providing the basis for temperature measurement using thermometers. The first law of thermodynamics is the law of energy conservation, stating that energy cannot be created or destroyed, only transformed. It is mathematically expressed as, whereas the change in internal energy is the heat added to the system and is the work done by the system. This law explains energy transfers in engines, refrigerators, and biological processes. The second law of thermodynamics introduces the concept of entropy, a measure of disorder or randomness. It states that in any energy transfer or transformation, the total entropy of an isolated system always increases. This explains the irreversible nature of natural processes, such as the spreading of heat, the mixing of gases, and the aging of living organisms. The second law also establishes the direction of spontaneous processes, stating that heat flows naturally from hotter to colder objects and not in the reverse direction without external work. This principle sets the efficiency limits for heat engines and refrigerators, as formulated by Carnot's theorem. The third law of thermodynamics states that as the temperature of a system approaches absolute zero, 0 Kelvin, its entropy approaches a minimum value. This implies that it is impossible to reach absolute zero in a finite number of steps, explaining why superconductivity and superfluidity occur at extremely low temperatures. Thermodynamic processes can be isothermal, constant temperature, adiabatic, no heat exchange, isobaric, constant pressure, or isochoric, constant volume. These processes describe the behavior of gases in engines and refrigerators, governed by the ideal gas law. Heat engines convert heat into work by exploiting temperature differences, operating in cycles such as the Carnot, Otto, and diesel cycles. The efficiency of a heat engine is limited by the second law of thermodynamics. Refrigerators and heat pumps work in reverse, using work to transfer heat from a colder region to a hotter region. Thermodynamics is fundamental to understanding energy conversion, chemical reactions, phase transitions, and the behavior of matter at the macroscopic level. It is essential in engineering, chemistry, meteorology, and cosmology, influencing technology, industry, and environmental science. Level 12, Kinetic Theory of Gases. The kinetic theory of gases provides a microscopic explanation for the macroscopic properties of gases, such as pressure, temperature, and volume. It models gas particles as small, fast-moving objects that are in constant random motion and interact with one another through elastic collisions. This theory is essential for understanding the behavior of gases at the atomic and molecular level and forms the foundation of thermodynamics. According to the kinetic theory, the pressure exerted by a gas on the walls of its container is due to the countless collisions of gas molecules with the container's surface. Each collision exerts a tiny force, and the cumulative effect of all these collisions results in the macroscopic pressure observed. The frequency and intensity of these collisions depend on the temperature and volume of the gas. The temperature of a gas is directly related to the average kinetic energy of its molecules. As the temperature increases, the molecules move faster, and their average kinetic energy rises. This relationship is expressed mathematically by the equation, whereas Boltzmann's constant is the temperature in Kelvin, is the molecular mass, and is the average speed of the molecules. The ideal gas law is a macroscopic expression that relates pressure, volume, temperature, and the number of gas molecules. It assumes that gases consist of many particles that do not interact except through elastic collisions. The ideal gas law provides a good approximation for the behavior of real gases at high temperatures and low pressures, but deviates at extreme conditions. Real gases deviate from the ideal gas law at high pressures and low temperatures due to intermolecular forces and the finite volume of gas molecules. The van der Waals equation modifies the ideal gas law to account for these factors, providing a more accurate description of real gas behavior. The kinetic theory also explains the diffusion of gases, where molecules move from regions of higher concentration to regions of lower concentration. The rate of diffusion depends on the temperature and the size of the gas molecules. The diffusion process is a result of random molecular motion and is described by Graham's law, which states that the rate of diffusion is inversely proportional to the square root of the molecular mass. The mean free path is the average distance a gas molecule travels before colliding with another molecule. It is inversely proportional to the number density of molecules and the effective collision cross-section. The mean free path plays a key role in the viscosity, thermal conductivity, and diffusion properties of gases. The kinetic theory of gases has wide applications in various fields, including atmospheric science, engineering, and chemistry. It helps explain phenomena such as the behavior of air in engines, the diffusion of gases in the atmosphere, and the cooling of gases during expansion. Understanding the kinetic theory is crucial for designing efficient engines, pumps, and refrigeration systems. Level 13, Thermodynamic Processes. Thermodynamic processes describe the changes in a system's state variables, such as temperature, pressure, and volume, as it undergoes transformations. These processes are fundamental to understanding heat engines, refrigerators, and even biological systems. The key thermodynamic processes include isothermal, adiabatic, isobaric, and isochoric processes, each characterized by specific conditions of temperature, pressure, and volume. In an isothermal process, the temperature of the system remains constant. According to the first law of thermodynamics, the heat absorbed by the system is entirely converted into work, with no change in internal energy. The work done during an isothermal process is given by where and are the final and initial volumes respectively, and is the number of moles of gas. Isothermal processes occur in idealized engines, such as the Carnot cycle. An adiabatic process involves no heat exchange with the surroundings. The system's internal energy changes only due to work done on or by the system. For an ideal gas undergoing an adiabatic expansion or compression, the relationship between pressure and volume is given by where is the adiabatic index or heat capacity ratio. Adiabatic processes occur in many real-world applications, such as in the compression of gases in engines. In an isobaric process, the pressure of the system remains constant while the volume changes. During this process, heat is added or removed from the system, resulting in a change in both temperature and internal energy. The work done in an isobaric process is given by where is the constant pressure. Isobaric processes are common in systems such as gas heaters and pressure cookers. An isochoric process involves no change in volume. In this process, all the heat added to the system goes into increasing its internal energy, resulting in a change in temperature. Since the volume is constant, no work is done during an isochoric process. The heat added is directly related to the change in internal energy, given by where's the change in internal energy. Isothermal processes are often modeled in closed, rigid containers, where volume does not change. The combination of these processes leads to thermodynamic cycles, where a system undergoes a series of processes and returns to its original state. The Carnot cycle, for example, consists of 2 isothermal and 2 adiabatic processes, providing an idealized model for heat engines. The efficiency of a thermodynamic cycle depends on the type of processes involved and the temperature differences between the hot and cold reservoirs. Each thermodynamic process has practical implications in engineering and technology. For example, isothermal processes are used in refrigerators and air conditioners, while adiabatic processes are key to the operation of turbines and compressors. Isochoric processes are found in internal combustion engines, and isobaric processes occur in steam engines and gas heaters. Understanding thermodynamic processes is essential for optimizing the performance of engines, improving energy efficiency, and developing new technologies. These processes govern the conversion of heat into work and the transfer of energy, which are central to the operation of power plants, engines, refrigeration systems, and many other technologies. Level 14. The Laws of Motion. The laws of motion, formulated by Sir Isaac Newton, describe the relationship between the motion of an object and the forces acting on it. These fundamental principles laid the groundwork for classical mechanics and are crucial for understanding the behavior of objects in motion, from falling apples to planetary orbits. There are 3 main laws: the first, second, and third laws of motion. Newton's first law, also known as the law of inertia, states that an object at rest will remain at rest, and an object in motion will remain in motion at a constant velocity unless acted upon by an external force. This law explains why it's difficult to change the motion of an object. For example, a car in motion continues to move unless the brakes, external force, are applied. The second law of motion is the law of acceleration, which states that the force applied to an object is equal to the mass of the object multiplied by its acceleration, or. This law explains how the velocity of an object changes when it is subjected to a force. For instance, pushing a car causes it to accelerate, but a heavier car requires more force to achieve the same acceleration as a lighter car. Newton's third law states that for every action, there is an equal and opposite reaction. This principle explains the interactions between objects. When you push against a wall, the wall pushes back with an equal force in the opposite direction. Similarly, a rocket propels forward by expelling gases backward, creating thrust due to the reaction force. These 3 laws are foundational to understanding motion and force in both everyday life and complex systems, such as the movement of celestial bodies. They form the basis of classical mechanics, influencing everything from the motion of vehicles on Earth to the trajectories of spacecraft in space. One of the important consequences of Newton's laws is the concept of momentum, which is the product of an object's mass and velocity. Momentum is conserved in a system with no external forces. This is why, for example, a moving train has a lot of momentum and is difficult to stop, while a small object at the same speed would be much easier to stop. The laws of motion are applied in engineering, physics, and even biology. They help engineers design structures and vehicles, scientists predict the behavior of planets and particles, and even help us understand human movements and biomechanics. Newton's laws work well in everyday situations and for objects moving at moderate speeds and in non-extreme conditions. However, they do not account for objects moving at speeds close to the speed of light or objects in very strong gravitational fields. For these cases, Einstein's theory of relativity becomes necessary. Level 15. Work and energy. Work and energy are core concepts in physics related to the ability of a system to perform tasks or change its state. In a mechanical context, work is done when a force acts upon an object and causes it to move in the direction of the force. The amount of work done is calculated as the product of the force and the distance over which it acts, whereas the force and is the displacement. Energy is defined as the capacity to do work. There are many forms of energy, such as kinetic energy, the energy of motion, potential energy, stored energy due to position, thermal energy, energy related to the temperature of an object, and chemical energy, stored in bonds of molecules. The total energy of a system is the sum of all forms of energy within it. Kinetic energy is given by where is mass and is velocity. This equation shows that the kinetic energy of an object depends on both its mass and the square of its velocity. This explains why it's much harder to stop a large truck than a small car traveling at the same speed. Potential energy, on the other hand, is energy stored in an object due to its position in a force field, such as gravity or elasticity. For example, an object held at a height has gravitational potential energy, which is converted to kinetic energy when the object falls. The potential energy is given by where is mass, is gravitational acceleration, and is height. The work-energy theorem states that the work done on an object is equal to the change in its kinetic energy. This principle explains various phenomena in mechanics, such as how a car accelerates when a force is applied or how a ball slows down when it is caught. Conservation of energy is a fundamental principle stating that energy cannot be created or destroyed, only transformed from one form to another. In any isolated system, the total energy remains constant. This principle allows us to analyze various physical processes, from simple machines to complex systems like heat engines. In thermodynamics, work and energy are also associated with the flow of heat. Heat is a form of energy transfer that occurs due to a temperature difference, and when heat is added to a system, it can do work, such as expanding a gas in a cylinder to lift a piston. Energy conservation plays a crucial role in everyday life and technology. From mechanical devices like levers and pulleys to electrical systems like motors and batteries, understanding how energy is transferred and conserved allows for the efficient design of machines and systems. Level 16. Power is the rate at which work is done or energy is transferred. It measures how quickly energy is converted from one form to another or how fast work is performed. Mathematically, power is defined as the work done per unit time, whereas power is work and is time. The SI unit of power is the watt W, where 1 watt is equal to 1 joule per second. Power plays a key role in various fields, from mechanical systems to electrical circuits, and is crucial in determining the efficiency and performance of machines. In mechanical systems, power can also be expressed in terms of force and velocity. For a moving object, power is given by where is the force and is the velocity. This shows that for a given force, increasing the velocity results in more power. For example, in a car engine, increasing the speed of the car requires more power to overcome friction and air resistance. Power is also important in electrical systems. Electrical power is the rate at which electrical energy is consumed or produced. It is calculated using the formula, where is the current and is the voltage. In an electrical circuit, the power dissipated as heat, light, or mechanical work depends on the voltage applied and the current flowing through the circuit. This principle is used in designing electrical devices such as light bulbs, motors, and heaters. In terms of energy conversion, power efficiency is a key factor. The efficiency of a machine or system is the ratio of the useful power output to the total power input. The higher the efficiency, the less energy is wasted. For example, in a power plant, the goal is to maximize the conversion of fuel energy into electrical energy while minimizing losses due to heat, friction, and other factors. In everyday life, power is often measured in horsepower, HP, a unit commonly used for engines, especially in cars. 1 horsepower is equivalent to approximately 746 watts. The concept of horsepower helps people understand the capabilities of engines and machines. A more powerful engine can do more work in a shorter amount of time, such as accelerating a vehicle faster or lifting a heavier load. Power generation and distribution are central to modern society. Power plants, whether fueled by fossil fuels, nuclear energy, or renewable sources, generate large amounts of electrical power which is then distributed to homes, industries, and businesses. The capacity of a power plant is measured in megawatts, (MW) or gigawatts, (GW), with larger plants producing billions of watts of power. The study of power is also important in understanding energy sustainability. Renewable energy sources such as solar, wind, and hydropower generate electricity through natural processes, providing clean power. Understanding the power generation capacity and efficiency of these systems is crucial for transitioning to a sustainable energy future. Level 17. Conservation of energy. The law of conservation of energy is one of the most fundamental principles in physics. It states that energy cannot be created or destroyed. It can only change from one form to another. The total energy of an isolated system remains constant over time. This principle applies to all physical processes, whether mechanical, electrical, chemical, or nuclear, and is essential for understanding how energy flows and is transformed in different systems. In mechanical systems, the conservation of energy is demonstrated by the conversion between kinetic energy, potential energy, and work. For example, in a pendulum, the total mechanical energy, the sum of kinetic and potential energy, remains constant, with energy continuously transforming from one form to another as the pendulum swings. At the highest point in its swing, the pendulum has maximum potential energy and zero kinetic energy. At the lowest point, the potential energy is converted to kinetic energy. The conservation of energy principle also underlies the concept of energy efficiency. In any energy transformation process, some energy is always lost, usually as heat due to friction or other inefficiencies. In ideal systems, all the energy would be converted into useful work, but in real systems, there is always some energy dissipation. For example, in a car engine, chemical energy from fuel is converted into mechanical work, but a significant portion is lost as heat. In thermodynamics, the first law of thermodynamics is essentially a statement of the conservation of energy. It says that the total energy of a system is conserved, and any energy added to the system as heat or work must be balanced by a corresponding change in the system's internal energy. The law of conservation of energy is crucial in understanding how engines, refrigerators, and even biological processes work. In nuclear reactions, energy is also conserved, although the forms of energy involved are more complex. In nuclear fission, the splitting of an atomic nucleus releases a large amount of energy, which is converted into heat. In nuclear fusion, energy is released when smaller atomic nuclei combine to form a larger nucleus. Both processes obey the conservation of energy law, with energy released as radiation, heat, or work. The conservation of energy principle is widely applied in engineering, technology, and environmental science. Engineers use this principle to design more efficient machines and systems, ensuring that energy is used as effectively as possible. For example, understanding the energy losses in power plants, transmission lines, and vehicles helps improve their design and operation. In ecology, the conservation of energy helps explain the flow of energy through ecosystems. Energy enters ecosystems primarily through sunlight, which is captured by plants during photosynthesis and passed along the food chain. Level 18. Work Energy Theorem. The work energy theorem is a key concept in classical mechanics that describes the relationship between the work done on an object and the change in its kinetic energy. It states that the total work done on an object is equal to the change in its kinetic energy, or, where is the work done, is the change in kinetic energy, is the final kinetic energy, and is the initial kinetic energy. This theorem is a direct consequence of Newton's second law of motion and provides a powerful tool for analyzing the motion of objects under the influence of forces. The work energy theorem is particularly useful when analyzing objects that experience constant forces. For example, if a car is accelerating along a straight road, the work done by the engine to accelerate the car results in an increase in its kinetic energy. By calculating the amount of work done, we can determine how much the car's velocity has increased. This theorem also helps explain how energy is conserved in a system. When a force is applied to an object, it does work and transfers energy to the object. If no other forces, like friction or air resistance, are acting, the object's kinetic energy will increase and the total energy of the system remains constant. In situations where forces vary over time, the work-energy theorem can still be applied by integrating the force over the distance the object moves. This allows for a more detailed understanding of how work is done in complex scenarios, such as in variable force environments, like the motion of a projectile under the influence of gravity. The work-energy theorem is also important in understanding the concept of power. Since power is defined as the rate of work done, it can be expressed in terms of kinetic energy change. The faster an object's kinetic energy changes, the more power is involved in the process. This is critical in applications such as engines, where maximizing power output is essential for achieving high performance. In real-world applications, the work-energy theorem is often used in engineering to analyze the energy transfer in mechanical systems. For instance, it helps engineers design systems like shock absorbers, springs, and lifting devices that rely on the conversion of work to kinetic energy. The theorem is also foundational in fields such as sports physics, where athletes apply forces to improve their performance. For example, a sprinter's work done during acceleration increases their speed, and the energy exerted can be analyzed using the work-energy theorem to improve training techniques and performance. Finally, the work-energy theorem is instrumental in understanding collisions and impacts. In elastic collisions, the total kinetic energy of the system is conserved, while in inelastic collisions, some kinetic energy is converted into other forms of energy, such as heat or sound. The work-energy theorem helps quantify these changes and predict the outcome of collisions in various contexts, from car crashes to particle physics experiments. Level 19. Power and energy conservation. Power and energy conservation are two closely related concepts that are fundamental to understanding how energy is used and managed in various systems. Power, as discussed earlier, is the rate at which work is done or energy is transferred. Energy conservation refers to the practice of using energy more efficiently and reducing waste, while power conservation involves reducing the amount of power consumed over a given time period. One of the most important principles related to energy conservation is the law of conservation of energy, which states that energy cannot be created or destroyed, only transformed from one form to another. In practical terms, this means that in any system, the total amount of energy remains constant, but it can change forms, such as from kinetic energy to heat energy, or from chemical energy to electrical energy. In many systems, energy conservation is achieved by reducing losses, particularly losses due to inefficiency. For example, in power plants, a significant amount of energy is lost as heat. By improving the efficiency of power generation and transmission, less energy is wasted, and more of it can be converted into useful work. Similarly, in household appliances, energy-efficient designs reduce the amount of power required to perform tasks like heating, cooling, and lighting. Power conservation is particularly important in electrical systems, where the demand for electricity can fluctuate depending on the time of day, weather conditions, and other factors. During periods of peak demand, the grid may become strained, leading to higher costs and potential shortages. By implementing power-saving measures, such as using energy-efficient lighting and appliances, consumers can reduce their overall electricity consumption and alleviate strain on the grid. In transportation, energy conservation is a key goal for reducing fuel consumption and minimizing emissions. Vehicles that are designed to be more fuel-efficient require less energy to travel the same distance. Technologies such as hybrid and electric vehicles are examples of innovations that contribute to energy conservation in the transportation sector, helping reduce dependence on fossil fuels and decrease environmental impact. On a larger scale, energy conservation also plays a critical role in addressing global challenges like climate change. By reducing energy consumption and shifting to renewable sources, societies can reduce carbon emissions and lessen their environmental footprint. Governments, organizations, and individuals all have roles to play in adopting energy-efficient practices, whether through regulations, technological advancements, or changes in behavior. Energy conservation is also linked to the concept of sustainability. Sustainable energy practices involve balancing the use of natural resources with the ability to regenerate them. By conserving energy and using it wisely, we can ensure that future generations have access to the resources they need while maintaining a healthy environment. In industries like manufacturing and construction, energy conservation is an ongoing effort to improve processes, reduce waste, and lower costs. By implementing energy-efficient technologies, such as more efficient machinery, better insulation, and optimized production processes, companies can lower their energy consumption and contribute to sustainability efforts while improving their bottom line.